So, up to now we have been looking at the equation u dash equals a of ut. So, now we will look at the inhomogeneous equation. So, V Banach, A dV contained in V infinitesimal generator of a C0 semigroup S of t greater than or equal to 0. So, now we consider a function f from 0 t into V given mapping. So, we investigate the solutions of the following equation u dash t equals a of ut. This is what we are looking for. Now, we will have an extra term f t. So, 0 less than t less than capital T, u of 0 equals u 0. Okay. So, this is equation which we want to look at. Okay. So, definition, let f from 0 t to V be continuous. A function u from 0 t to V is a classical solution of star if u is continuous on 0 t, continuously differentiable on the open interval 0 t, ut belongs to dA for all 0 less than t less than capital T and star is satisfied. Okay, so this is called a classical solution. That means everything is fine and you can solve the solution exactly. Okay. So now let us assume that u is a classical, let u be a classical solution of star. So we will get a representation for u. Okay. So now consider, define W of s equals s of t minus s u of s, 0 less than or equal to s less than or equal to t. Now, a and s commute, we know, on dA of course, obviously, and therefore we have W dash of s equal to minus a s of t minus s of us, u is in d of a. Okay. So, when you differentiate this, you get minus a s of t minus s us, and therefore, a will come here, actually a of us you will get, but then a and s commute. Okay. Plus s of t minus s u dash s. So, I have just used the product rule. Okay, and that is equal to minus a s of t minus s of us and what is u dash s, we substitute for it. So, plus s of t minus s a of us plus s of t minus s fs. So, these two will get cancelled because of the commutativity. So, that will give you s of t minus s f of s. So, if you integrating, you get W t minus W0 over 0 t. Okay. So, you get Wt minus W0 equals integral 0 to t of S of t minus s Fs ds. Okay. And therefore, W, so Wt is what? So, if you Wt is S of 0 u of t. So, that we will get Ut, that is Ut equals W0. W0 is nothing but S of t u of 0. Okay. So, S of t u of 0 plus integral 0 to t S of t minus s Fs ds. Okay. This is called the variation of parameters formula, and this is similar to whatever you have done for linear equations in ordinary differential equations. This is exactly how you would have written. You have the integrating factor and then which is e power something, and that is exactly how you get this. Okay. So, this is the generalization of the usual variation of parameters formula which you have in ordinary differential, linear ordinary differential equations. Okay. So, this is called, so solution can be written in terms of this. So, this in fact, so the solution is given like this, therefore implies solution unique since you have a representation formula. Okay. So, remark, if f 0 t to v is such that is integrable, then RHS of double star makes sense. Okay. And therefore, you, this is called then this is called a generalized solution or mild, this different terminology used in different books, and therefore generalized or mild solution of star. So, then let us say instead of this, let us say double star is called a generalized or mild solution of this thing. Okay. So, a generalized solution always exists if you have integrability, but it may or may not be a classical solution. So, let us give an example of this. Okay. So, let x belong to V such that St of x is not in dA. So, if x is not in dA, this can happen. Okay. So, otherwise St of x is always in dA. Okay. So, for all t greater or equal to 0. Now, you take f of t equals St of x, then f is continuous and hence integrable. Okay. So, now you take u0 equal to 0, which of course belongs to the domain of A, and then the generalized solution is ut equals, so this will be 0, s of t minus s ffs, ffs is sfs x. So, s of t minus s and sfs, that will give you composition will give you s of ts x, which will be come out of the integral, and therefore this will be giving you. So, this is equal to integral 0 to t s of t minus s sfs x ds, which is equal to s of t x integral 0 to t ds, which is equal to s of t times st of x. But u t equals t times st of x is not differentiable. since you have st of x does not belong to dfa, and therefore this is not differentiable, we know, and therefore you have that u, so implies u is not a classical solution. So generalization, so generalized solution will always exist, and but it may not be a classical solution. So when will we have a generalized solution is a classical solution? This is the question which we want to ask. So we now have the following theorem. Let f from 0 t to b be continuous, and let v of t equal to integral 0 to t s of t minus s f of s ds, 0 less than equal to t less than equal to capital T. Okay. If star admits a classical, a unique classical solution, then 1, you have t going to Vt is continuously differentiable on 0 t, and 2, Vt belongs to dA for all t in 0 t, and t going to A of Vt is continuous on 0 t. Okay, proof is very simple. Okay, so u is a classical solution and u of 0 equals u0 in dA. Then ut is equal to st of u0 plus Vt. Now st of u0 belongs to dfa, ut is also in dfa because you have a classical solution. So this implies that Vt belongs to dfa, and also you have this is st of u0 is also in dA, Vt is different, continuously differentiable. Because ut is continuously differentiable, u0 is in domain of A, and therefore stu0 is also continuously differentiable, and therefore Vt has to be continuously differentiable. So that shows that the first one is Vt is continuously differentiable, and also Vt is in D of A. And now finally we have A of Vt is equal to A of ut minus A of st u0, and that is equal to u dash t minus ft minus d by dt of st of u0, and this is continuous. Okay, so A of Vt is also continuous, and that completes the proof. Now though we said 1 and 2, actually 1 if and only if 2, they are equivalent statements. Okay, so assume 1 true. Okay, then look at sh of t, sh minus identity by h of v of t is equal to 1 by h integral 0 to t s of t plus h minus s f of s ds minus integral 0 to t s of t minus s f of s ds, okay, and that is equal to 1 by h of integral 0 to t plus h s of t plus h minus s f of s ds minus integral 0 to t s of t minus s f of s ds and minus 1 by h integral t to t plus h s of s t plus h minus s t plus h minus s f s ds. So, they are just adding and subtracting, changing and so on. Okay. So, 0 to t plus h, 0 to t, t to t plus h, that is how I have written this. So, that is and that is precisely equal to v of t plus h minus v of t divided by h, okay, minus 1 by h integral t to t plus h s of t plus h minus s f of s ds, and now we know v is differentiable, one is true. So, this goes to v dash t, and then this should go to the lower value with h equal to 0, and therefore t equals s, this will be s of 0 minus f of t. Okay. So, this implies that Vt belongs to d of a and a of Vt equals v dash t minus f of t, and therefore, you have that you have this also. Okay, so, this implies 2, which is continuous, therefore, this implies 2. Okay. Now, 2 is true. Conversely, then what happens? You have that the above computation implies that d plus of Vt is equal to a of Vt plus Ft. That is what the same computation you do. Now, you know that this is in d of a, so you get a of Vt, take Vt to s, and this will give you just d plus Vt instead, and this is continuous. Okay. So, d plus Vt is continuous implies d minus Vt exists. We have seen this many times before, and d plus equals d minus, and therefore, v is continuously differentiable. And therefore, implies 1. Okay. So, 1 and 2 are equivalent to each other, though we proved them separately. So, now we have the following theorem. If either of the equivalent conditions 1 or 2 holds, then the generalized solution double star is a classical solution of star. Okay. So, we were asking the question, when is the generalized solution a classical solution? So, if one of these conditions is true, then that means both are true, then you have that the generalized solution is a classical solution. So, proof. So, we have Vt belongs to dA, and if u naught is in dA, then ut equals st of u naught is also in dA, and therefore, you have ut equals st u naught plus Vt belongs to dA, and you have a of ut equals a of st u naught plus a of Vt equals d by dt of st u naught plus du by dt dv by dt minus ft, the old computation whichever we did, and that is equal to u dash t minus ft. So, u dash t is equal to a of, this is v dash t plus, so this is the whole thing is u dash t, okay. So, a of ut plus ft, u of 0 equals u0, and this completes the proof, okay. So, we will give a corollary of this, gives you a concrete application of this result. Let f belong to C1 of 0t with values in V. Then star has a unique classical solution for every u naught in D of U. So, we just have to show that one of those conditions is true. So, proof. So, we write Vt. So, we have to show that this is continuously differentiable, that is all we have to show. So, Vt is equal to integral 0 to t s of t minus s fs ds. Now, I can also write this by change of variables to s0 to t s of s f of t minus s. Okay, I am going to put t minus s equal to tau, and therefore, when t is equal to 0 you get t, when t is equal to t, s equals 0 you get t, s equals t you get 0, and then the ds is minus, so the integral remains 0 to t, this becomes tau, s is equal to t minus tau, and therefore, I have this, okay. So, if you like, this is just a change of variable, okay. So, if you do not like the s here, put a tau. Okay. So, now I am going to try to differentiate this, we differentiate the under the integral sign. So, you have v dash t is equal to, so you first have to evaluate this at t and then differentiate t, which is give you 1. So, st of f of 0 plus integral 0 to t of s of tau f dashed t minus tau d tau. I am just differentiating this with respect to t. So, s of tau f dash t minus tau d tau. So, this is just in differentiation under the integral sign is well defined because f is in C1. Okay. So, this integral can be differentiated, and therefore, this is what you have, and therefore, this is continuous, and now you can rewrite it again if you change the variable once more. This will give you s of t minus s f dash s ds. Okay. So, once again you make a change of variable and you get this. So, now this is continuous on 0 t. So, v dash v is a continuously differentiable. So, the first condition is satisfied, and therefore, implies generalized solution is classical. Okay. So, this is about the inhomogeneous equation. Now, this inhomogeneous equation is very important in the study of control theory. This is where the control theory begins, and therefore, you have this equation is very important.